Okay, when it comes to factoring trinomials, this is a great case of working backwards through a problem to solve something. So, for example, we have all seen what happens when you take two binomials like x plus 2 and x minus 5 and multiply them together. You may have done this in various ways. You might have distributed this twice. So x plus 2 gets distributed to the x. It also gets distributed to the minus 5. And then, of course, we can distribute the x to both of those terms. To get x squared plus 2x, we can distribute the negative 5 to both of those terms. To get negative 5x and minus 10. And then we can collect our like terms, which is 2x minus 5x, to get negative 3x minus 10. Another way you might have done this, and perhaps this is faster, is to realize that using the distributive property twice, you create four terms. The first one comes from the product of the first terms of each binomial. The last one comes from the product of the last terms of the two binomials. And this middle term, right, which is the sum of these two terms, is the sum of the inner product and outer product, right? So the 2 and the x here and the negative 5 and the x. Okay, so this is abbreviated F for the product of the two first terms, O for the outer terms, I for the inner terms, and L for the product of the last terms, FOIL. You may have heard of that acronym before. It's just a way to kind of shortcut this process. But you can see here that if we're starting with this and trying to get back, right, we can use our knowledge of where these numbers came from to accomplish that. So for example, if I started with x squared minus 3x minus 10, I could make an assumption that it's the product of two binomials. The first ones, the first terms of these two binomials, have to multiply together to give me x squared, so I might make an assumption that they're both x. That seems fairly reasonable. The last terms of the two binomials have to multiply together to give me this negative 10. So I've got some possibilities there. 1 and 10 might work, or 2 and 5 might work. And we know which one it is, right? Because we just did it a second ago. It's going to be the 2 and the 5. But if we're working backwards, and this is where we started with, we'd have to consider both possibilities. We also know that because we got a negative 10, if I'm looking at these two terms, or these two terms, one of them will have to be positive, one of them will have to be negative, right? If they were both negative or both positive, this would have been a positive product. Further, I've got this middle term of negative 3x, right? That middle term came from that difference of terms. Of course, had that been a positive 5, that would have been a sum of terms. So I can look at the inner product and the outer product and say, is there any way I can combine those, addition or subtraction, and get a 3 or 3x? Okay, so that in combination with the fact that they have to be different signs, and hence we're looking at subtraction, there's no way to make this work, right? 1x and 10x. There's no way to get 3x out of that by adding or subtracting. However, 2x and 5x, is there a way to get a negative 3x? Sure. You take the 2x, make it positive, and the 5x, you subtract it. And now we're back to where we started. Okay? So this is the idea of factoring trinomials. Assume it breaks into two binomials. Make some good guesses for the first terms. Remember the last terms, the product has to give you this. We can do a sign analysis here and say, well, if that's negative, they got to be different signs, these two last terms. If it's positive, they have to be the same sign. And this has to be some sort of combination of the inner and outer products. Either those things added together or subtracted together. Okay, so let's work some examples. Number 1. We'll start off simple. X squared plus 3x plus 2. Here again, I should always check, is there a common factor I can pull out of all the terms? There's not here, right? X is not on the last term. 2 and 3 don't show up on all three terms. But it's something to check. It'll keep their numbers small if it happens. So, failing that, let's try to break this into a product of two binomials. In considering what I want to put in the front of those two binomials, remember their product has to give you x squared, so x and x seems like a pretty decent guess. In considering what I need to put at the end of those two binomials, remember the product of these two values has to give me 2. I don't have many options. 1 and 2 is pretty much all I can worry about. Maybe -1 and -2, right? This sign is positive. The only way to get a positive 2 is if they're both the same sign, so they're either both positive or they're both negative. But remember the middle terms, 1x and 2x, have to combine to give 3x, a positive 3x. The only way that can happen is if this is plus and this is plus. Those two binomial factors, are of course completely factored, so we're done. That's x plus 1 times x plus 2. Let's look at another one. How about x squared plus xy minus 6y squared? Here again, look for a common factor. Look to see if it's maybe a special product, a difference of squares, or a sum or difference of cubes. None of those things apply here. So let's treat it like a trinomial and assume it breaks into the product of two binomials. The first guys of those two binomials have to multiply together to give x squared. Again, x and x seems like a very reasonable assumption. The last two guys should multiply together to give us -6y squared. It's not a constant like we had above, but not too hard to guess some possibilities. One might be a single y and 6y. Another possibility might be 2y and 3y. Okay, let's consider both. This negative tells you, again, the product of these two things has to give you -6y squared. If that's negative, one of these two guys is negative, one is positive. Or one of these two guys is negative and one is positive. The middle term tells us that if we add the inner product and the outer product, let's see, we've got a yx and a 6yx. And depending on the signs here, we might be adding or subtracting. Is there any way we can take a single yx and 6yx and get a single yx? That's not going to happen, no matter what these signs are. What about down here? 2yx, 3yx. Is there any way to, and again, depending on whether these signs are positive or negative, we may be adding these things, we may be subtracting these things. Is there any way we can take 2yx and 3yx and get a single xy or yx? Sure. We could add the 3yx, that's the outer product, and subtract the 2yx, that's the inner product. And sure enough, negative and positive, that's going to give us a negative third term. Okay? There he is. There's our factorization of our second example. Let's look at a third. 6x squared minus x minus 2. Here again, we have no common factors amongst all three terms. Doesn't appear to be a difference of squares or a perfect square or difference of cubes or sum of cubes or any of those special products. So we treat it like we're factoring a regular old trinomial. Assume it breaks into the product of two binomials. The product of the first terms of those binomials has to give us 6x squared. So now we've got some choices to make, right? Maybe that's 6x and x. Maybe that's 3x and 2x. Okay. We'll leave both possibilities up for the moment. This last term, remember, if we look at the n terms of the binomials, Their product should give us this negative 2. Not too many options here. We could have a 1 and a 2. We could also have a 2 and a 1, right? Maybe I'll list that just to the side here. 6x and a 2 and an x and a 1. There's a couple reasons why this could be discarded pretty quickly. One is if you put the 2 here, there's a common factor of 2 to both of these terms that could be pulled out. That would imply there was a common factor of 2 here, but there wasn't. So that's one reason we can just kill that off directly. Another is if we actually consider putting in pluses or minuses here, there's no way to get a negative x, right? You have a product of 2x and a product of 6x. You can't add or subtract those together to get a single product, excuse me, a single term of negative x. So this is out, okay? Remember where we were. We were looking at what we could put at the ends of these binomials to create a negative 2 here. 1 and 2 are pretty much the only factors we need to worry about, with the possible exception of their sign. We might have a 1 and a 2 here. But again, do you see the problem? 2x and 2. There's a common 2 you could pull out. Same problem we hit over here. So I don't want to put them in that order in this problem. But we could also consider 2 and 1. Okay? That doesn't suffer from the same problem. Now, looking at these remaining 2 possibilities, look at the inner product and the outer product. Here we have 12x and a single x. Is there a way I can combine those things via addition or subtraction, depending on these signs here, to get a single x that's negative? Again, 1x and 12x? No way. That's out. What about here? 4x and 3x. Wait a minute. If I want a negative 1x, I could subtract the 4x and add the 3x. Voila! That works. 3x times 2x is 6x squared, minus 4x plus 3x is negative x, and negative 2 times positive 1 is negative 2. There's my factorization. And of course, neither one of those linear factors factored any further. Okay? Let's do one more. X to the 4th plus 7x squared plus 12. Here again, there's no common factors amongst all 3 of these terms. It doesn't appear to fit any special products. It's not a difference of squares. It's not a difference or sum of cubes. It's not a perfect square of a binomial or any of those others. So we make an assumption. Suppose it's the product of 2 binomials. What could I put here and here? Well, the product of the first elements of the binomials has to give you x to the 4th. Now, there are a couple different ways to do this. X squared times x squared seems most natural, probably. You could also have x to the 3rd times x to the 1st, or x to the 4th times 1, I suppose. But generally, that's going to create more than just these 3 terms. So let's go ahead with x squared and x squared, and if it doesn't pan out, we can always try something else later. The last terms, remember, have to multiply together to give you 12. Here we have several possibilities. We could use a 1 and a 12. We could use a 2 and a 6. We could use a 3 and a 4. Okay? Now, which one of those things is going to be most beneficial? Remember our middle term, 7x squared. That has to be the sum or difference of the inner product and the outer product. Well, here we have a single x squared combined, either via addition or subtraction, with 12x squared. 1x squared and 12x squared. Any way to get a 7x squared out of that? Nope. That one's out. What about 2x squared and 6x squared? Let's see, if we added them, we could get 8x squared. No. If we subtracted, we could get 4x squared. No. So that one's out. What about this one? 3x squared and 4x squared. Aha! If we added those two things, if we took positive 3x squared plus 4x squared, that's going to give us 7x squared. And their product, both being positive, is positive 12. That's our winner. Okay, again, it is worthwhile to double check very quickly, are these two factors themselves completely factored? They do involve squares after all, they're not linear, but they are, right? We're dealing with the sum of two squares, and those very rarely factor. Okay, all right, so that's it.